So, I call me Som, and I work in Google. I'm working in Google for the last 2.5 years, and I'm working as a data management specialist in India. So I've been working on Postgres and the other open source database for the last 10-12 years, and I started my career in Oracle years back. So I've been primarily working on Oracle. Now I'm helping customers to migrate from Oracle to Postgres mainly and optimize PostgreSQL deployment in various managed services or in on-premises. So today we'll look into the advanced performance tuning, and these are the few topics which we'll go through. We'll look into the database flags, and we'll look into the important database flags with respect to Oracle, because there are a lot of customers and a lot of folks who are migrating from Oracle to Postgres. And sometimes they want to set the PostgreSQL parameters, the flags, very similar to what it is there in Oracle. And they do not have the PostgreSQL experience. And the default parameters and flags are not that much optimized with the current workload the customers have. So we'll look into some Oracle flags and their equivalent in Postgres and what we can do to tune them. We'll look into checkpoints, commits, and their impact on performance, because checkpoints or commits are the most resource-intensive operations which happens in any RDBMS. Then we will look into 5 use cases where I worked with customers, very unique use cases where we were able to reduce the query planning time because the performance issue was happening because of excessive time doing the query planning. We'll look in how to optimize join methods, join orders. We'll look how to optimize.
We'll try to improve.
Thank you. Thank you. Yeah. Am I audible now? Thank you. I was shouting and most of the energy was going in the first slide itself. Anyways, glad everyone is able to hear. So we'll look into 5 use cases on reducing query planning time, optimizing the join methods and join orders, optimize queries on partition tables, optimize parallel queries, and there was a very strange use case on the full index scan. So these are the 5 use cases which I, when working in Google, have faced across 5 customers actually who had recently migrated to PostgreSQL. It does not matter whether you migrate to the Google managed services or some other CSP managed services or on-premise Oracle, Postgres. So basically these are the things, these are the use cases which any customers or the performance issues where any customers can face. So we'll look into the parameters and flags. So like I said, we'll compare the parameters and flags between Oracle and Postgres because many of your customers and many of you are probably trying to migrate Oracle databases to Postgres. Yeah. So when I speak to customers who are working as Oracle DBAs, they have a lot of confusion and a lot of doubts on the equivalent PostgreSQL parameters and flags which they need to set according to their current Oracle initialization parameters. So this is basically a like-to-like comparison between the Oracle and the PostgreSQL flags and what we can do to optimize these flags to basically cater to the particular workloads of the customers. Okay. So first are the memory related parameters. Like in Postgres, like in any other RDBMS, there is always the shared memory and there is the per process memory. So in Oracle, that is basically managed by SGA target, and in Postgres, it is managed by the shared buffers, where basically there is a shared portion of your memory which is allocated to store your data blocks and index blocks which are concurrently accessed by the backend processes and also by the background processes. So in most of the clouds, in most of the managed services, the shared buffers is usually set between 30 to 50% of RAM, and sometimes you will need to increase it. Okay, you can increase it up to 70% of RAM. so that you get optimal performance. Usually when you are seeing that your Oracle database is, you do not have a very high buffer cache hit ratio, or your SGA, you had a very large SGA. So if you just move to Postgres and keep the default parameter, which is somewhere between 30 to 50%, it may not give you performance. Okay, there could be a lot of caching or a lot of data file rise which could be happening. Even the backend processes may be writing the data blocks during reads, because we know, we'll look into it further down after some slides, that the database blocks or the index blocks are not only written by the checkpoint process, the background writer, but also by the backend processes. When you do not have free buffers to read into blocks from your disk into the shared buffers, so rise can also happen. So you need to set the shared buffers properly. Then in Oracle, there is another parameter, memory target, which is a new parameter which was introduced in Oracle version 11G release 2 mostly. And basically this is a combination of SGA target and PG aggregate target in Oracle. So in Postgres, this is a combination of your shared global buffers, which is shared buffers, and your per process memory, mainly the work mem and the maintenance work mem. Okay, usually the maintenance work mem is by default set to 4 MB, and maintenance work mem by default is set to 64 MB. And usually you do not get a lot of benefit by setting the default value, especially when you are processing large ETL workloads, where you are doing large vacuuming, or when we are restoring the databases, because, or basically when you are doing the maintenance operations. Even when the vacuuming, when you do not set the auto vacuum work mem, the memory is allocated from the maintenance work mem, and the basically if you have number of auto vacuum max worker processes, so whatever you set from the maintenance work mem, that is multiplied by the auto vacuum work mem, and it is allocated from the maintenance work mem. So if you are doing large vacuums, or if you are doing index rebuilds, even an altered table like adding a foreign key constraints take memory from the maintenance work mem. So in most likely, you have to increase your maintenance work mem from its default 64 MB. So in most of the production databases, I have seen it being set to few GBs, like 1 GB, 2 GB. It depends how much of RAM if you have in your system. The same thing with the work mem. And the another parameter which is not often discussed is the hash mem multiplier. So in the work mem, the memory you are giving to the individual processes when it is doing sort joins, when it is doing sort merge joins. So it will do that operation into the memory, otherwise it will spill into the disk. And you always have, whenever it goes to the temp files in disk, there is always a chance of increased IO. So you have to set work mem properly, and you are doing, if your workload is such that you are doing a lot of hash operations, hash based joins, hash based aggregates and everything, you also need to increase the hash mem multiplier. So what I've seen that mostly if you set between 4 to 6, it gives you a good performance when your workload is doing a lot of hash join, because that gives you the amount of memory, okay, multiplied by the memory which you are given for work mem. Say for example, work mem you have set to 64 MB, and you set hash mem multiplied to 2. So basically you give 128 MB to your hash join operations. Val buffers. Val buffers is very important, especially for your write intensive workloads, because when we update or when we write into a PostgreSQL databases, the first thing, not only it modifies the data pages or the index pages in the shared buffers, but it generates the redo or the write ahead log. Those val records gets written into the val buffers, and then it gets written into the file system cache or the kernel cache, then it gets flushed into the disk. So any commit, when the synchronous commit is set by default, is the local val writes and the val sync which basically happens. So if your val buffers, so there are two, we'll look further into the, once we go down into the checkpoints, we'll look that there are two very important functions. The xlog insert record, which basically inserts the val records into your val buffers, and that is done by the backend process by default. So if you do not have enough val buffers, the backend process basically need to write certain filled buffers into the kernel cache, and that is not desirable because the backend process is holding the locks, exclusive lock onto the data pages into your shared buffers. So it is not desirable that the backend process, your server process is actually writing the filled val buffers into the buffer cache. So we will see some wait events related to val buffering. So for what we have seen for high concurrent, write intensive workloads, you can easily increase the val buffers to 64 MB or 128 MB. By default, it is only 3% of your shared buffers. We'll look into the checkpointing parameters later because there is a couple of slides specifically on checkpointing. But in Postgres, the important parameters in checkpoint is the checkpoint timeout and the max val size. The checkpoint timeout by default is 5 minutes and the max val size by default is 1 GB. And various cloud service providers, they are playing around with the checkpointing parameters. Somewhere it is set to 1.5 GB, the max val size, somewhere it is set to 5 GB. And certain cloud service provider, for their few managed database offerings, they do not give you the option to change the checkpointing parameters because they have optimized the checkpoint, or in few cases they have eliminated the need of checkpoints also. But it is very important because by default your checkpoint will happen either every 5 minutes or till your max val size gets filled, and checkpoint is extremely IO intensive operation. So we should control the checkpoint timeout and max val size in a way that your checkpoints happen ideally somewhere between 2 to 3 minutes. It doesn't happen, but make sure that it does not happen every 10 or 15 seconds because you will see a lot of checkpoint related wait events. You can use still PostgreSQL 16, you can use the PG stat BG writer actually to look into your checkpoint, and it's sometimes confusing because there are three processes which are doing checkpoint: the checkpointer, the background writer, and the backend processes. Though the checkpointer and background processes are different processes, but they all are doing checkpoint. And in Postgres 17, we have the PG stat checkpointer, which just caters to the checkpoint which is done by the checkpointer processes. And you can sometimes when you want to troubleshoot checkpointing, because when you set PG wait sampling, you want to see the wait related events to checkpoints, you will see a lot of wait events on data file writes, data file flush, and data file sync. And you will also see the checkpoint timer also. Basically we see a lot of wait events on that. So when you want to see how frequently you are doing checkpoints, you can always set lock checkpoints to on. And configuring the IO related parameters, I think first I'll talk on the random page cost. So random page cost is basically, this favors your index scan because this is something which governs how your small random reads will be, the cost of small random reads which is seen by the optimizer. So when we look into the history of PostgreSQL, the random page cost was always set to 4. That is with respect to the sequential page cost, because in those days the disk, it was magnetic disk, okay, and there used to be a lot of time in the disk rotation and disk seeking time and everything. So in those days the cost of accessing doing random reads was thought to be like, when there are a lot of tests which were performed, 4 times faster, 4 times slower than the sequential page access. But given now we have faster disks, we have SSDs, we have cache, and we have very, very fast disks and disk at lower cost, the random page cost should not be set more than 1.5x times than the sequential page cost. So in all the production databases which I have been working on in the last many years, I've seen the random page cost being set somewhere between 1.1 to 1.5. You should not be setting it lesser than the sequential page cost because that might have detrimental performance effect, because in that, until unless your workload is very small and your index is entirely cached into your shared buffers or into your kernel cache, your random page cost should not be less than the sequential page cost. So ideally we should set it somewhere between 1.1 to 1.5. And the another parameter which is overlooked is the effective IO concurrency. So basically most of the Linux systems now, most of the operating system is suppose asynchronous IO. So with effective IO concurrency, it basically tells you how many concurrent IO requests can be done in parallel. Okay, now this basically affects the bitmap scan. So if your queries, if your workload is such that it is doing a lot of parallel bitmap scan, you will see a performance hit if you do not set effective IO concurrency high enough. So ideally you should be setting it to few hundred depending on how fast your disk are, but most of the cases all the operating system supports asynchronous IO. So it's very important to set effective IO concurrency somewhere between 200 to 500, I would say, especially to improve the performance of the parallel bit scan. Yeah, and here I believe I have already spoken about the random page cost and the so another parameter is effective cache size. So the random page cost and effective cache size, the values of these parameters define your access method, whether it is going for the full table scan or whether it is going for the index scan. So basically lower the value of random page cost and higher the value of the effective cache size, it will favor index scans. Sometimes what happens, even we see that you have all the proper indexes built, you have run the vacuuming, okay, and basically you have created, you have gathered the statistics with the proper sampling size, I mean by changing the default statistics target to a high value, okay, and the indexes are not fragmented. Sometimes indexes still do not get picked, and these two parameters are very important. Like if you go and increase the effective cache size, provided you have enough RAM and enough buffers which are allocated at the kernel buffers, you can easily increase the effective cache size. Now a trend which is happening in most of the cloud service provider in the managed services, you will see the effective cache size is set pretty high. It is almost set to 1.5 or 2x times the size of the RAM. And please bear in mind, it does not actually allocate that memory to the index. It just gives an estimate to the planner that this amount of data cache both in the shared buffers and the kernel cache is available for the index scans actually. And I believe, and another why this is important parallelism, because I do not see any production workloads where there is no parallelism, okay, and these parameters, the max parallel workers, max parallel workers per gather, these are very important about how many parallel server processes are being spawned by Postgres to do your parallel operations, parallel selects actually. So by default, what I have seen, when you move to managed services, okay, your parallel max servers, your parallel workers per gather, and these 2 or 3 parameters which are related to parallel processing are set very conservatively. Okay, we should ideally set it to half or 3/4 to the number of virtual CPUs which you have, whether you are running Postgres on-prem or your managed services. We should set it to a high enough value, not high enough that there is basically again resource starvation. We'll see another use case where setting it to very high enough, very high value also caused performance issue. And cursor sharing, will look into that, because in Oracle cursor sharing, because when you move from the Oracle database to Postgres, mostly you set cursor sharing to exact, similar or force. And the equivalent parameter in Postgres is the planned cache mode. That is how you want to utilize your cursors, whether you want to have a custom plan or you want to have a generic plan. So we'll look into that. When you want to have a custom plan, it means that for every different bind variable which is passed, the plan is being generated again and again. Okay, that is very good if you have very skewed data distribution. But when you have very uniform data distribution, okay, and you are passing a lot of parameterized values, it does not make sense to generate a execution plan for every different bind variable values that is passed. In that cases, a generic plan is much better because it saves you on your planning time. And we look into max logs per transaction. This is important when you are basically querying a lot of partition tables. Say for example, you are querying your orders and line items tables, okay, where you are storing say weekly order or monthly order, you know, querying for 3-4 years. So the problem here is that by default the DML logs per transaction is set to 64. So if you are touching tables or even the partition tables more than 64, your query will time out, your query will error out. So look into these use cases also. Yeah, now coming to the second topic, checkpointing and commit in PostgreSQL. This is very important, not only in Postgres but in any RDBMS. And we'll see that many of the cloud service providers, including like Google or AWS or Azure, they are optimizing on checkpointing. They are optimizing on commit, because these are very IO intensive operation and also CPU intensive operations, and they are coming with managed service offerings which eliminates checkpoints also, because checkpoint, like I said, the more you, if we eliminate checkpoint, okay, you always get better performance. Now there are two very important parameters which determines the checkpoint. One is the checkpoint timeout and the max val size. Like I was talking previously, the max val size, the default value of 1 GB is never sufficient for a production workload which has very high DML activities, because within few seconds you will have more than 1 GB of val segments which gets generated. So checkpoints will happen every few seconds, and that is not desirable. And also, if your shared buffers are not basically sized properly and your checkpoints is not able to keep pace by flushing the dirty buffers, it is the backend process also, when they are doing a select, they will need to do a checkpoint, okay. And there are three processes which does checkpoint: the checkpointer process, the background writer, and your backend processes. So it is always desirable that the checkpointer process does the checkpoint, and it's also important that the background writer supports the checkpoint process when the checkpoint process is not doing the checkpoint, so that it also regularly flushes the dirty buffers. So it's important to tune not only the checkpoint timeout and the max val size, but also few parameters related to background writer, how frequently it does the checkpoint and how many dirty pages it flushes actually. And sometimes we'll also the checkpoint missed alert in the PostgreSQL log. That is nothing to panic, because sometimes when your database is not active, even when the checkpoint timeout happens by default, which is 5 minutes, okay, so your checkpoint will be missed. Your checkpoint doesn't happen. It is not necessary that the checkpoint will happen every 5 minutes. So ideally, make sure, this is the utopic world to have checkpoint every like 3 to 4 minutes, but I would say, like we have seen in 95% of the cases, a lot of performance improvement when we were able to have the checkpoint frequency somewhere between 60 to 90 seconds. And we should never have checkpoints every 10-15 seconds. So we should strive for something by setting these parameters to have checkpoints every 1 to 2 minutes, 1 to 1.5 minutes. This is an example, like on the I believe the right hand side, if you see the default, so basically by default, apart from the checkpointer process, so when there is excessive checkpoints, and we'll see the wait events, we'll see data file rise, data file sync wait events, and we'll also see a lightweight lock on, we'll also see a val write wait events, a lightweight lock, not the val writes. So the val write wait events can be of two types. It can be an IO wait event and a lightweight lock. IO wait event is when the backend process is basically writing the buffers into the kernel cache, doing the val write. Or if you have set the asynchronous commit, if it is done by the val writer process. Okay, but there is a lightweight lock also which is taken by the checkpointer process. It also happens in Oracle because it has to update the checkpoint change hash into the val writes. It has to create a checkpoint record into the val record. So if excessive checkpoint is happening, it can also wait on this lightweight lock. On the lightweight lock type, which is you will see as val write, apart from high values of data file writes and data file sync. So if you see that, and if you look into PG stat BG writer, and you compare, if you have Postgres 17, if you also look into the PG stat checkpointer, you can find out how much checkpointing the background writer is doing, and you can also see whether there is a view where you can see there where the background writer was stopped actually because it has flushed too many buffers, because by default the background writer will flush not more than 100 dirty buffers and they will sleep for 200 milliseconds, which means that they will keep on flushing 100 dirty buffers and then sleep for 200 milliseconds, which are governed by the BG writer delay and the BG writer LRU max pages. So if you see on the left, this is for the customers where we have actually changed it. Okay, for BG writer delay 50 to 100 milliseconds is a very good thing when you have very write intensive workloads and you are seeing very high frequent checkpoints and you are seeing checkpoint related wait events. Even after setting the checkpoint timeout and the max file size to the desirable value also, still you are not able to tune the checkpointing that much, and still you are seeing wait events and still you are seeing some latency in the application. If you set your BG writer delay somewhere between 50 to 100 milliseconds and the BG writer LRU max pages somewhere between 200 to 300, for write intensive workload you will see a very good performance improvement, because BG writer will be doing, the background writer will be flushing those dirty pages more frequently and in greater extent, and it will help the checkpoint process actually to have less IO activity when the checkpointing happen. So these are two important parameters also which are not that much looked into. We usually look into the checkpoint timeout and the max file size, but we should look into this. In fact, Google managed services very recently in the last like few weeks back only, they opened these parameters for editing, because many of the managed services in different cloud service provider do not allow you to change the BG writer delay and BG writer LRU max pages, because if it is not tuned properly again, okay, it can again be detrimental to performance. So we have to validate everything by the wait events. We should go through the proper methods of changing the parameters which we have talked, and then we should change it. But now many service providers for the managed services are opening these parameters for editing. Now commit in Postgres. So commit in Postgres, again like checkpoint commit, they go hand in hand. Okay, we should try to reduce the commit and we should not try to have the excessive commit in Postgres, and val buffers plays a very important role, because just last week there was a customers who they were using very high write intensive workload, okay, and their val buffers by default is like 3% of shared buffers, and for them the shared buffers was set to 30% of RAM. So basically just imagine 3% of 30% of your RAM, that is how much your shared buffers is getting. So what was happening is that when I looked into the wait events, it was basically the backend processes, it was not getting enough val buffers actually, free val buffers. So the backend process was constantly writing few of the filled val buffers into the kernel cache, and this happens because that backend process is already holding access exclusive lock to the data pages, because you are doing some DML, exclusive lock on the data pages because you are in DML, so that page is locked. So this basically created a cascading effect, and lot of transactions were basically blocked because it was a hot block contention and the val buffers were not sized properly. So by default, we in production database we do set synchronous commit. Okay, I do not see any cases except few exception where you turn off synchronous commit. So your transaction gets committed when both val writes and
basically val rise and val sync happen. I'm not taking into account the standby, because there also you can configure the remote val rise, remote val sync and all those things. So it's just a pure primary database where your transaction gets committed when the val sync also happens. And these are two main important functions, like the x insert, x log insert record, and the x log flush, which does the insert of the val records into your val buffers, and the flush is also been done by the backend processes actually doing a transaction commit. And the xlog insert record, that function should not be doing any val writes. The val rise and the val flush is a function of the xlog flush. So if you set up pg waste sampling, and you can find out which particular val functions are doing those things. So if you say if you find out that the val writes is being done by the xlog insert record function, so there is something wrong. Okay, either your too much of DML activities are happening, and most probably your val buffers are set very low. So needs to increase the val buffers, and usually the ideal setting of val buffers is somewhere between 32 MB to 128 MB. Like 64 MB is a safe bet actually. Now if we set off synchronous commit, okay, so the val write and val flush is not done by the backend process. Just not happen in Postgres, also happens in MySQL also, where you basically turn off synchronous commit. It is not done by the backend process. It is always done by the background process actually. Here it will be done by the val writer process, and that will happen every 200 milliseconds for when you set synchronous commit to off, because val writer delay by default is set to 200 milliseconds. So but we should not worry about so much of turning on synchronous commit unless it is absolutely necessary. Okay, commit delay is something which might help you, because you can set at the session level, at the database level. It might help you when you are doing a lot of bulk insert. Okay, when you're doing a lot of bulk insert and you want to bash those commit, you want to increase the throughput, that will help, because that is the delay in microseconds which is introduced between a transaction commit and the val flush that happens. Yeah, and here I want to talk about the val segment size, because in Postgres 16, if you see, the val segment size has been increased from 16 MB to 64 MB, and in our test, in our labs in Google, what we have seen that we do see a performance of 10 to 20% improvement for various workloads with an increase in the val segment size, because in higher value of val segment size will make your log switches and archiving less aggressive actually. So that is something. So if you are running on-premise Postgres, so like if you are running any version of Postgres less than 17, let's say 16, 14, whatever, if you increase the val segment size, you will get the benefit. Okay, if you set it to 64 MB, but in managed services you cannot increase it, but definitely on-premise Postgres you definitely should increase the val segment size, and that is the reason this has been increased in Postgres 17. Yeah, this is now we'll talk about 4 or 5 important use cases. Okay, the first one is the plan cache mode. So like I said earlier, the plan cache mode by default is auto, which means your custom plan will be used. For every different bind variable value, a new plan will be generated. Now just imagine if you are executing a query hundred of times per second, and from a particular API, and multiple APIs are hitting your database. Okay, and you are passing a lot of parameterized values. So what will happen? Every time your new execution plan will be generated for every bind variable passed, which is good if every bind variable value is a different representation of the data distribution, if you have skewed data distribution. But it is absolutely not good when you have a uniform data distribution, because the first bind variable values passed is the correct representation of the data. So the first plan which gets generated should be optimal for all the different values of bind variables when you have uniform data distribution. So in that case, for the uniform data distribution, plan cache mode should be set to generic. And we have seen the use cases where, if you see, the planning time is basically 35 milliseconds and execution time is 1 milliseconds, and it was a banking customers and their banking transactions, they were getting latency, and this it was causing outages, and we were breaking our heads and everything. We were looking into the execution plan, we are looking into everything, the access method, the access type, the join order, join methods, everything. But initially we didn't look into the planning time. All of a sudden it came to our eyes that okay, the planning time is high. Now this is an example. This is from this customers, where you can see where we simulated this, and we are seeing different bind variables which are passed. On the left hand side you can see the plan cache mode has been set to the generic plan, and after setting it to generic plan, where the planning time was around 35 milliseconds, that came into 1 milliseconds, because this is very important, where you can reduce your planning time, because you have forced a generic plan now. So first time when the plan got generated, it is reusing the plan for different parameterized or different values of the bind variables which you're passing. So that reduces your planning time, and this basically solves the problem. This is another parameter which is overlooked, the join collapse limit and the genetic query optimization. Because see, join collapse limit, so basically the join collapse limit by default is 8, which means, see, by default what happens is that when we write complex queries, okay, so the optimizer will basically flatten out this, join orders into a series of from list, and beyond, by default it is 8, so beyond 8 from list items, it will stop flattening out the join orders. So what happens is that for very complex queries, if your join collapse limit is by default 8, which is less, you do not get an optimal execution plan, because all your join orders are not evaluated properly, which means you will not get proper join methods. So this was the case. If you see, traditionally the Postgres, the servers were running on not that powerful hardware, okay, we had limited CPU clock cycle speeds, limited RAM and everything. Now with higher clock cycle speeds, higher and more powerful processors, okay, more powerful RAM, especially more powerful processors, it's extremely fast. So the planning, we should utilize the planning time, we should try to utilize more join orders. So what we have seen, if you set increase the join collapse limit from its default value to 8 to maybe 12, 16 or 20. In our case it was set to 20, and we'll see in the next slide that for 20 execution time from 20 minutes came down to basically from 8 minutes came down to less than 1 second. The same thing with the genetic query optimization. With the genetic query optimization, what happens is that okay, it does the planning generation or the join orders by doing the heuristic searching. By default it is exhaustive searching. Exhaustive searching takes lot of time. So with the genetic query optimization, when you do basically heuristic based searching, your join or your planning time is faster. But sometimes when you join very complex queries, okay, your planning time can be faster, but you can get suboptimal plan also, because you are not doing the exhaustive search planning method, you are joining using the heuristic planning. But sometimes that outweighs the increase in planning time which you get when you want to join a lot of tables, okay, with the exhaustive search planner. So by default the GEQO, genetic query optimization threshold, is set to 12, because like I said, older processor and everything. Now you can easily set it to 16 or 18, because now we get faster processor and everything. So which means that beyond, suppose you set it to 18, so it means that beyond 18, okay, when you expand the query, when you basically flatten those from clause, the join orders and everything, beyond 18 it will try to use the genetic query optimization. It means you are getting more option to do basically exhaustive search planning to get better execution plan. So this is one example. Top of the screen you see, with the join collapse limit by default which is set to 8, you can see the number of rows and the time which it takes, and it is using the sort merge join. Then we change the join collapse limit to basically 20, I believe. Join collapse limit was changed to 20. I think 20 or 40, I don't remember top of the mind, but it was definitely changed to 20. So the query, you see, more join orders were evaluated, you get a better join method. So the sort merge join is not there, now you have the nested loop join because it had the index, so it was iterating through the index and you get the nested loop join. So the higher value of join collapse limit, which should be set now because you have faster, better CPUs, you get more join orders to be evaluated and basically you get better execution plan. Coming into max log per transaction, like I said, the default value is 64. Okay, sometimes when you are querying lot of tables and lot of partition tables, which is the case, okay, suppose sometimes you want to use you're partitioning your data. Sometimes when you want to run analytic queries on your transactional databases, you want to query basically selecting from the partition table. So if it is set by default 64, you will see the errors that no space for adding more locks held by the PID. Okay, so everything is fine, the execution plan is fine, okay, everything is fine, the statistics is fine, but you are seeing query latency because you are joining more than 64 tables or table partitions and you cannot acquire more logs actually. So best practices in partitioning, I would stress on the last two: enable partition wise join and enable partition wise aggregate, because in Postgres by default these two are turned off. Only partition wise pruning is turned on, but partition wise join and partition wise aggregate is turned off by default. Again, this is coming from the classic background that when Postgres was running, the servers were not that powerful. Okay, to have partition wise join, partition wise aggregates, it takes a lot of CPU cycles. In those days, like 8 or 10 years back, okay, it was very detrimental to the performance because the planning time used to take more. Now basically when you are joining partition tables, okay, see, when they have equal partitions, okay, partition like both the tables are partitioned by range and they have equal partition, so basically you join the matching partitions and then you append the result, which is much faster. But without partition wise join, what happens, you basically select from the individual partitions of the partition tables and then you append it. At the end you have the hash operation, and basically it does only the hash operation, the hash based join. And what happens is that when you are appending the different partitions from different partition tables and then doing a hash operation, you are doing on a large data set, and that is extremely time consuming, extremely CPU consuming, extremely high memory consumption. So this is another example. So on the left hand side, if you see, the partition wise join is turned to off. Okay, and if you see, I'm querying two tables, okay, which has three partitions. Now if you see, the individual partitions are queried, okay, and then it is appended and the hash condition is happening at the top, t2.b is equal to t1.a, and these are equal partition tables. Basically they have matching partitions. Now with partition wise join, if you set it to on, okay, you can see that the matching partitions are being joined. Okay, here they have been joined using the hash join basically, but if you have a matching, if you have an index, it can join, it can use the nested loop join to join these matching partitions. Then it does the hash, at the end it does the append. So that's the advantage. So this we are doing on a I tried it out on a small data set with few million rows. If you see, we got almost 2x improvement. Just imagine if you have partitions with say hundreds of millions of rows or billions of rows, how important or how much of performance improvement you will get with partition wise join. And optimize parallel queries, I would always say set max worker process and all these processes properly. Sometimes when you set it very high, you can see a wait event call on the execute gather, because the parallel coordinator process is a single threaded process. Now if you have lot many parallel workers per gather and it is pushing to the parallel coordinator process which is single threaded, okay, you will definitely see wait events on execute gather. So it is important to set these parameters appropriately. Okay, maybe 50% of your virtual CPUs or the number of CPUs you have, but not that high also. Say you should not be setting 32 parallel workers and parallel workers per gather to say 28 on a 16 or 8 virtual CPU machine. This is a interesting case. I think this is the last case which I'm talking about, so I'll maybe take 2 minutes here. So uh, is index only scan always good? Yeah, it is good. 90% of the case is good because it is not doing a heap fetches, right? It is getting your data by querying your indexes. But at times index only scan is not useful. I have seen in 2 or 3 customer cases where they were facing production issues because they were going on index only scan, because they created, now we have different indexes to create. Now you can you create partial indexes, you create covering indexes and everything, so that based on your filter condition you want to go with the index only scans. But if you see in this cases, it was doing a heap fetches. So why index only scan would do a heap fetches? Okay, it is because the index only scan relies on your visibility map. So if all the pages on your visibility map for which the index is searching the data is basically true, means it is visible, so it need not do the heap fetches. But here if you see, there are 2 pages, because I have updated, this is a use case which I generated, I have updated 1 row. So basically 2 pages were not visible. One is the old value of the row on page 0 and one is the new value of the road at the end road. If you see, there are 2 pages where I've used the PG visibility map function where it is count of 2. So if you see all visible from PG visibility map, the relation name is SOM. If you see the page number 0 and page number 5408 is not visible, and that's the reason it is doing 186 fetches, because the first page I believe it has around 185 rows and the last page has 1 row. So index only scan is not always helpful. So if you see a lot of heap pages, it means that your visibility map is old. So vacuuming plays an important role. So vacuuming not only help you on clearing the dead tuples to prevent transaction ID wraparound, okay, it also updates your visibility map. And so these are the basic housekeeping, just to end it. So maybe just so vacuum regularly, auto vacuum, tune those auto vacuum parameters, okay, analyze regularly. When you analyze with a good value of default statistics target. Maybe have extended statistics, have column statistics, have multivariate statistics, create relationship between columns, say between the city and zip code, okay, and create the correct index types, not only B tree indexes, maybe inverted indexes, maybe block range indexes, whatever. And have connection pooler when you are having a lot of small bursty connections, and keep monitoring in place. And that's it. And maybe you can we have the EMEA database community in Google, which we are having on a monthly basis, okay, and this is something where everyone is interested, where you can join, because now we are investing a lot on AI. We can talk about here, we will have talks on AlloyDB and how we are using AlloyDB and our Cloud SQL Postgres in Google to build RAG application, how we are using the models build and how we are doing vector embeddings, how we are calling models from your Gemini, how we are calling models from the Anthropic or the Hugging Face. So we'll have lot of discussions there. We have discussions on Postgres and everything out here, which we have started from this year, so it will be a good thing for everyone to join. So that's it from my end. I would be happy to take any questions. Thank you.
Any questions? Okay, it looks no questions, so somebody
I think.
Sorry.
Will the slides be available on the P2D2 website?
Yeah, I can upload.
Okay, somebody thank you for the storm of the deep insight.
Yeah. Thank you everyone. Thanks everyone for your time. Thank you everyone. I appreciate it.